Hello everyone. We have Armen today. He is a research scientist at Fair, where he has been working on multimodal language models. His work includes contribution to projects like Encoder, CM3, scaling laws for mixed model LMs. Before his research on multimodal language models, he worked on improving and better understanding fine-tuning approaches for large-scale language models. Prior to joining FAIR, he was an applied scientist at Microsoft working with Turing team, focusing on pre-training for learning universal representations. Yep, Armin, I think you can start.
Yeah, sounds good. So I'm going to start off a little bit broader than the current paper. So this is kind of a highly opinionated, personal opinion presentation on kind of large language models in general, why we think scaling laws are important, and kind of the future of AI research. So let's start off, I guess, with some preliminary kind of definitions. So I feel like this slide gets updated every time I give this talk. It's kind of when we talk about large, what we talk about now is kind of 30 billion parameters trained on over 400 billion tokens. And so language models, I think most people here will be familiar with, but we're just modeling the joint distribution of text. And the models are usually just post-norm variants of transformers. I rarely see people kind of going outside of this architecture. And so really the success to large language models, kind of it's in the name, has been scale. And so there's kind of fundamental questions that we have to ask when we talk about scale. Fundamentally, how do we scale? Like, what is the correct parameterization of transformers? Like, there's many hyperparameters, right? Do we have a larger embedding space? Do we have more attention heads? How do you balance parameter counts between attention and feed-forward layer? We have questions that some papers try to answer, like if you have a fixed compute budget and data budget, what is the optimal parameter budget? How do you balance data? There's just a ton of complex questions that really we don't have good answers for. And because of that, I kind of have this strong claim that as of now, scaling large language models is mostly an art. And so fundamentally, we need to make this science. So as of now, everything that we do is kind of based off of gut intuition. Like ramping someone up on large language model training, if you look at like AWS costs, is a really, really expensive exercise. Debugging model training is not formalized. Usually what you do is you just trust the senior research scientist who knows what they're doing. And you take their word, right? Like we don't have formal ways to debug anything. Distributed computing is hard, but a few people have begun solving them. And kind of, I put this out very explicitly, like I don't think anyone fundamentally understands what they're doing when they're training large language models. They just have intuitions about how to properly train them. And so because of that, I think there's a reason why all of the large language model startups, like including Cohere, right, all have people from big tech training their models, where they kind of use the compute that's available in big tech to ramp up. And then they kind of go and start up their own companies. So kind of to reinforce my point, I want to kind of tell two stories about large language model training. So the first one is like a very prototypical case of like we ask one of our junior researchers to run like a language model training, and you usually end up with these questions, right? Like this guy, he works really hard. He pings me at 2 a.m. saying that the 1.3 billion OPT is giving him some weird convergence when he's trying to train him on new data. And then the back and forth we kind of have is like we go through kind of a checklist of things that can potentially be wrong. Again, none of this is foundational. I'm just guessing off of previous intuition what potentially might be wrong. You can kind of even see my comment that this is all guesswork at this point. Eventually, we find the right issue, which was around some like loss scaling, and the atom betas that were selected were a little bit wrong, and then the convergence issues are kind of magically fixed, right? So this is a very common kind of happens on a weekly, if not daily basis, kind of here affair for people who are training large language models, especially when we try to ramp people up. Everything is kind of based off of this gut feeling, right? And then there's like even harder problems to solve that are in distributed computing, or when you're working with a lot of nodes, or one node failure can kind of cause cascading effects. So this is a story that I was not directly involved in. I was kind of a fly on the wall, but sometime during last year, we kind of saw really bad throughput issues. So we saw that like our words per second would significantly drop and then increase and then drop. And so this is kind of you can't stably train a model when you have these significant throughput issues. And when I say we, the people involved in this group, I was kind of, again, a fly on the wall. And the cloud service, they ruled out everything that was obvious, right? Like we debugged the training code. We made sure GPUs were saturated. We looked at like memory transfer bottlenecks. We looked at all the painful CUDA stuff that could have potentially been going on, and we couldn't find anything. And then somehow it magically resolved itself, right? And then it turns out that the problem was that, you know, our cluster that we were training on was in Phoenix, and there was this heat wave in Phoenix, and I guess the cooling, you know, in this cluster wasn't up to par, so we would see throughput drops purely because the temperature in Phoenix was too high, right? And so we went to the you know, to the cloud service, and they literally had to put the equipment into an oven in order to reproduce how hot it was getting in Phoenix, in order for us to check off that, hey, you know, this is the real reason why we were having trouble with our large language model training, right? So there's kind of this very long tail of problems in large distributed computing that is very complex to solve if you haven't worked on large language model training before. And this gets to kind of my next point, which is that the goal right now should be to try to make training large language models a science. And there's been a ton of good work, right? So starting with like Kaplan's seminal paper, we start off by asking kind of very fundamental questions, right? So if you're going to debug how your language model is training, you need to be able to answer like a fundamental question, which is, you know, what is the expected loss that you think you will get if you know the model size, or if you know the data set size, or if you know the compute size. So kind of this was Kaplan's kind of very first scaling law paper, where these questions were answered. And then people started answering kind of more complex questions. So for example, you can potentially answer the question like, what is the expected loss if you know both the model size and the data set size? So these were the scaling laws that were introduced in you know, the Chinchilla paper. And so the breakdown of the parameterization of the scaling laws kind of differs from every scaling law paper. So you know, Kaplan's scaling law paper was just a standard kind of power law distribution. And then the Chinchilla paper offers this kind of, for me at least, a more intuitive parameterization, which is you break down the loss as there being some minimal achievable loss. So this is kind of the natural entropy that exists in the text, plus 2 errors. So one error that you get from the functional approximation, which is a function of, you know, the number of parameters that are in the model. And then you get some kind of optimization or convergence error, which is a function of the number of data points that you have. And so if you put this all together, you kind of get this new type of parameterization for scaling laws, and it turns out that this is quite a good fit. And these Chinchilla scaling laws gave us what we call compute optimal scaling laws, in a sense that we can say, you know, for some fixed compute budget, we know what model size and what data set size we should pick in order to have kind of a compute optimal with respect to complexity model. So kind of so far, all of the scaling laws that we've been talking about has kind of only been about text, right? So this is a little bit unfair because scaling laws and scaling law coefficients fundamentally matter on the data that you're training on. So when we talk about scaling laws, we're keeping this data variable constant, right? So what our recent paper was trying to answer was, you know, what do these Chinchilla-like scaling laws look like if you kind of go to a ton of modalities? Before moving on, I wanted to ask, like, are there any questions, or should we just save the questions for the end?
I think either way would work. So if anyone has any questions and we would like to have more interactive session, then that also works. Or otherwise, we can put the questions at the end as well.
Yeah, I mean, sounds good.
Yeah. So I was
Jump in.
just yeah. There was this one question. So I think there was this one paper from Mila, right, which was like broken scaling laws, right, where they show that there can be multiple parallel laws, right, like in basically in the graph, right. So do you think like it has also to do with like just the modality specific behavior, or like that is general trend, like that is maybe where they show that you can express still like scaling laws and across different things and just join it through like right. So under different trajectories, it is like just the same way as the Kaplan's law.
Um, I don't think the parameterization is necessarily needs to differ for different modalities. I think the coefficients are going to be widely different.
Okay.
Um, that's kind of my guess. You can imagine that there is some type of I don't know what you would call it, like a generalized scaling law that takes into account the uh, underlying data domain. So you can imagine that there's some information theoretic property of the data that will let you give very generalized scaling laws, which says, you know, this is the scaling of transformers on a data set with this like informational theoretic
I see.
coefficient. Um, but I don't think we're there yet, and I haven't seen papers that do this. I think it's quite complicated to
Okay.
do.
I see.
Now, what do you think about like the multilingual scaling? Like, does adding other languages is like proportional to adding one big if there's like database of 10 different languages of size, and like is it exactly the same as like having one big data set of same language?
Yeah. Okay. So that's an interesting question. Whether or not we treat multilingual as multimodal has been kind of a topic of debate for us. So one thing that I will say is that for small enough models, adding multiple languages hurts perplexity pretty badly, especially if you don't change the way that you tokenize or you don't change vocabulary size. Um, there is a point of diminishing returns here, though. So large enough models, I don't think have any issue modeling multiple languages separately. The coefficients will change because the underlying data will change, but it won't be as severe as you think. I think a great example is like if you look at Llama or OPT, like I think they weren't explicitly trained on any non-English data, yet they do quite surprisingly good on multilingual. These models are quite good at soaking up any type of multilingual data that exists.
I see. And yeah, just one question. So also, I think based on some papers, right, it is known that adding code data definitely helps, right? Like model generalize well. So do you think like this different sort of data, that the code data that we have, right? Like for that scaling loss as a different behavior, or like it just can be treated as a like a similar way, like adding new data, like one different other data modality. Just wondering.
Yes. So we definitely treat code, at least in this paper, we treat code as a different modality. Kind of, it has very different distributional properties, right? So, for example, there are some tokens in code that have kind of zero informational content, right? Like closing braces can be almost deterministically predicted, right? So
Yes.
the informational properties are very different. Now, it's a good question about whether or not like perplexity is like fine-grained enough of a metric to capture like reasoning, for example. I don't have an answer to that. But we have always treated code as kind of as a separate modality. And you're absolutely right. So like fine-tuning on code will give you better reasoning than just training on text.
Yeah,
So that has been consistent.
I see. And do you also distinguish maybe instruction tuned data sets with the like a standard, let's say, unsupervised or unlabeled corpus that we use for self-supervised learning pre-training? So maybe like instruction tuning, they treat it as a different modality, or like that this is maybe right.
Yeah, I mean, generally like supervised fine-tuning or like instruction tuning, to me is more like this is my claim. This is just this is intuition, but I would argue that like almost if not all of the knowledge that is learned by the model is learned during the pre-training stage, and that instruction tuning is just creating kind of like a communication API between the internal knowledge of the model and us humans and how we interact with this model. I don't think instruction tuning fundamentally learns any new knowledge or any new reasoning capabilities. It mostly just creates this API between humans and LMs. So
Yeah, sorry, go on. Continue.
I was going to say I don't think foundationally instruction tuning helps any kind of the underlying tasks that we care about.
Okay, I see. So it can be more of taught as in a way to like align models to human responses or some way, some sort of alignment, right? Like partly.
And I mean, of course, if you have a large enough instruction tuning data set, then sure, right? Like if you have 100 billion tokens of instruction tune data set, that kind of you start rivaling the pre-training corpora size, then yes. I mean, at the end of the day, I think it comes down to like bits of information, right? So per sample, I think the instruction tune data have more bits of information, but there's not a lot of them versus like training on 1.4 trillion tokens. There's like an order of magnitude difference of quantity of information between the instruction tuning or supervised fine tuning part of the pipeline versus the pre-training part of the pipeline.
I think that's a valid point. Right now, yeah, we don't have like instruction tune data sets in abundance for pre-trainings.
Yeah. So I guess I can keep going here. So kind of the very first thing that we did, right, was we went and we used up a ton of compute to produce chinchilla-like scaling laws for all of the modalities that were kind of interest to us. And so we picked 7. So we picked just modeling kind of unconditional images and then conditional image generation. It's like you can think of pretty much like DALL-E. Pure text, speech and text, which you can think of as doing like TTS or ASR, unconditional speech, code, and then molecules, which are just in the SMILES format. And so we went and we trained a ton of these models, and we saw that fundamentally they all behave in kind of different ways, and the underlying coefficients also paint a very different story about how scale looks like for these modalities. So we felt like we were onto the right path, because previous work will not be able to explain like 6 out of the 7 modalities. And then we started asking these questions, like, let's say we train a model that's concatenating the speech and text data, unconditional speech and text data sets. What do we think the scaling law parameterization will look like? And so what we propose is to kind of model this in an additive nature in the same way that kind of the chinchilla scaling laws were proposing. So you have kind of this term, which is the loss if the data sets were modeled completely independently. And then we have this term, which is kind of, again, this maximal level of synergy. Like, what is the most amount of loss that we can reduce when we have knowledge of both? And then you get some error terms that are very similar to the ones that are in chinchilla, which is, there's some type of competition that occurs in the functional approximation space. And then there's competition between modalities that occurs in this optimization process. And so we kind of get this very trivial kind of extension to chinchilla scaling laws that give us the ability to answer a lot of questions about training in this mixed model setting. And so we went and then we fit a ton of these kind of empirically across model sizes and across token sizes. And then this is when things get kind of interesting. Now we can start talking about modality competition. So if we are reducing the loss, the total loss of modeling 2 modalities beyond the independent modeling of the 2 modalities, then we can say that we are kind of synergistic, right? Otherwise, we say that the modalities are in competition. And using our coefficients, it's kind of very easy to tell where we are on the spectrum. So if you compare the kind of the synergy, if the synergy is greater than the loss, or is greater than the approximation error, then you can say that kind of we have synergy here, right? And so you can actually go out and try to break this competition barrier once you have the coefficients for all the mixed model scaling laws, right? So what we did is here, this is a plot of kind of a couple of different bimodal trainings. So you can see that, and let me say kind of this black dotted line for each one of these represents this kind of theoretical competition barrier that we fit with empirical data, right? So what we did is we said, okay, like I think the cheapest thing to break the competition barrier would be the speech text. So let's try to break the competition barrier for the speech and text modalities, right? So you get this really nice formula, which is minimize the flop count, which is this is a very nice formula that gives you kind of a nice approximation for flops for you to train on a model size with n parameters and d tokens, such that we are kind of breaking the competition barrier. So if you go and you plug this into the equations that we have, this will tell you that, for speech and text, we want, n, the number of parameters to be close to 30 billion and the data set size to be about 45 billion tokens. I think in the paper, we kind of rounded up just because these experiments are expensive and we wanted to actually break the competition barrier. So we actually see that, our scaling law prediction was kind of spot on, and that we actually do break the competition barrier. So this becomes kind of a cool example that we can use scaling laws to do very non-trivial predictions. In this case, predicting at what scale like two completely independent modalities would lift each other up. So yeah, this was quite cool to be able to do. And then so from there, actually, maybe let me ask if there are any questions before moving on to the next section of the paper.
So I had a question. So for example, let's say when we have like this multimodal loss, right? Like when training LLM, or at least having this more modality component, right? So it might be possible, let's say that the LLM greedily optimizes one or the other task, right? So how do you let's say account for that into the scaling loss? If
Yeah. So that's a good question. I think we'll touch upon this on the future slides. But I think you can kind of separate the micro and macro behavior. Kind of from the macro perspective, you're always minimizing the loss in kind of a very specific form, right? What happens between the individual modalities, I don't think matters too much to the scaling law, even though it's quite interesting, and we'll talk about it later. Also, I think the fact that we're optimizing a single loss, right? Like we're just optimizing token-based log likelihood, makes it that we can make these predictions without worrying about the underlying intricacies of the individual modalities. Does that make sense?
I think it does make sense. So for example, let's say if you have like this different loss components, right? And instead of just like this log likelihood, right? So if you have that way the formulation, then do you think that might have a implication on the scaling loss, or more ultimately it won't matter, as we just care about the final loss optimization, right? Like at least a trajectory.
Yeah, I mean, if you change the loss, the scaling loss will change too, right? So like, I don't know, if you remove the log likelihood from the images and then move to like a mean squared error loss, presumably the scaling loss will significantly change.
Okay. And that's the scaling loss at the moment right now. Let's say this is just a question. So right now we just take into account the total number of tokens, right? Like, but we don't differentiate or distinguish between the quality of tokens, right? Or at least how the learning might change, right? Depending on the quality of tokens. So how do we like go about that maybe? So for example, let's say certain out of my 100 billion corpus, right? Maybe 20 billion is like very high quality, or at least where tokens where the maximal learning contributes, right? And the other 80 billion is more of like the stage. So how do I then account that? Okay, that let's say based on this pattern, maybe if I have X quality of the high quality data, then probably this is how my scaling loss will behave. And if I have like, yeah, like it's a way, the point was that between like a trade-off between noise and quality, right? How do we define and like we try to account that into the scaling loss?
Yeah, I mean, that goes back to my original wish for scaling laws, which is that there's some information theoretic property the data that you can use. I don't know what that looks like. The kind of saving grace for language models here is because you have these very large batch sizes, and because you do this type of IID sampling, you kind of average out the very high quality with the very poor quality. And presumably every batch has about the same informational content, which is why these scaling laws, I think, are so predictable. But yeah, I'm not sure. I don't know what this information theoretic quantity is. It's very hard to find. Like, we've thought about it quite a bit. It seems that there's not something that's trivial. Like perplexity is not trivial, right? Like the perplexity of a very complicated sample and a sample that's random is going to be the same, right?
Yeah.
Yeah, but there's good work to try to figure out what data quality is. I'll give, there's one slide about future work that talks about this. So I can talk about it then.
Yep. Okay, again, that would be great.
Cool. Sounds good. Okay, yeah. So going back, we were wondering that, okay, so we can predict some nice properties of training, but can scaling laws fundamentally tell us more about the actual training of the language models, right? So the very first thing is actually what you just mentioned, is that we saw that there's this intermittent coordinate like training. I think this is a fancy title that for some period of time, for some non-trivial period of time, the training flatlines, like the loss flatlines for a specific modality. So here we say like different source modalities are optimized at different paces. So here's an example of like when we were training on speech and text modalities together. For about 10,000 steps, the perplexity on speech pretty much didn't improve at all. At the same time, the text perplexities were consistently monotonically decreasing. Yeah, don't really have much to say there except that this happens. We're not really sure why this happens. It doesn't seem like something that should happen, but it does. And kind of the really cool thing is that if you have scaling laws, the scaling laws are actually a function of this alpha ij parameter that represents the functional approximation error due to the competition, which makes more sense. So pretty much what this is saying is that if you have more competition, you will likely see more of this intermittent coordinate ascent-like training. Intuitively kind of makes sense. Again, fundamentally, we don't understand why this is happening. Another kind of very cool thing that we saw is that the optimal batch size for modalities is actually correlated with beta ij. And so beta ij is the coefficient that talks about the competition when it comes to data, the number of tokens property. Sorry, I think this definition here is wrong, so don't look at it. But what we found is that we can actually predict the optimal batch size if you know what this beta ij is for a pair of modalities. And so this is really weird, right? Because our scaling laws actually were learned with suboptimal batch sizes, and yet they are predictive of optimal batch sizes. So there seems to be something quite fundamental about actually having proper scaling laws. And again, to me, it doesn't make much sense why this would be the case. But it actually turns out to be quite useful. And I'll actually share some examples of, you know, if you have scaling laws and you have the proper kind of learnings about how to train, how significant of improvements you can get. I have a slide that talks about this in a little bit. And the next one was actually quite cool. One of the core problems that we have is when training large language models is that we get these gradient spikes that end up ruining training. So usually we have a lot of logic like skipping batches or lowering learning rate, or fixing your atom betas or increasing weight decay. We have a ton of ways to pretty much mitigate this. And so the thing that we found is that you can actually predict the rate of these deteriorating training dynamics if you look at alpha ij. Again, this is the parameter that measures how much competition there is in the functional approximation. And so we see something really interesting, which is that there is this like very strong empirical correlation between number of parameters and alpha ij and corresponding to the number of gradient spikes. So it makes sense. So we know that as we scale models, we tend to get more gradient spikes. And now what this is saying is that if you have more competition within your data, you will actually get more gradient spikes. And so this is kind of very predictive. So now when we do like language model training, we can predict how many gradient spikes we will see. If we have like an order of magnitude more than we expect, then we know that we're doing something. So now we have a lot of these really cool small debugging things that we can use to figure out whether or not we're properly training a language model. Before we move on, are there any questions? Or are we all good? Cool. Okay, so one thing that we tried out is we said, okay, you know what? We have these very nice scaling laws for you know, text and image or text and image. Can we go and can we retrain one of our models to fundamentally improve kind of the training, pretty much, right? And so we picked some of this works in this previous work, which was done by one of our interns here, which is called Retrieval Augmented CM3. Pretty much you can think of this as like DALL-E 1, but with retrieval augmentation. And so this paper that we wrote kind of came out before we had these scaling laws, so there was a lot of guesswork involved with how we trained this language model. And presumably the training here wasn't done completely the proper way, which is kind of expected because we didn't have this scaling laws. So we went back and we kind of used all the learnings that we got from the scaling law paper. You know, we took the optimal batch size. We were able to predict whether or not something is going wrong. So we were able to kind of get the right learning rate. And we were able to have kind of a very, very stable training for all of these models. And kind of the very interesting thing is that our 350 million model was kind of outperforming the original 2.7 billion model that we have, just because we had proper laws and we trained it in the proper way. And so this kind of got us very excited. So we trained much larger versions of it, and you can see like we are approaching kind of the state of the art in text to image without like there's no diffusion. We're not doing anything tricky here. This is like original DALL-E 1 with retrieval trained with proper scaling laws. And so if you do this, it turns out that you can be state of the art, right? And so here's like a couple of images that we get from sampling. So you can see, I think all these prompts are either from party prompts or from image gen. So you can see, I think the quality is quite good. I think it rivals some of the better models that we have. I'll give you kind of another example here, which is again all from party prompt or from image gen. And so it turns out that we can kind of get state-of-the-art text-to-image models with pretty much zero complexity just by knowing how to properly scale up decoder-only models for a specific domain. So this is why I think scaling laws are very important. And in some sense, I would argue before you do any type of like decoder-only log likelihood language model training, that you should probably get some scaling laws, fit some curves to them, of course if you have the compute to do so. This will give you kind of non-trivial gains when you train these models. Before I move on, are there any questions?
So I think I was just wondering one case. So probably in the original Kaplan et al. Paper, right? So they show more of like a, I'd say nearly linear trend, right? Like as you keep on increasing the compute or parameters and things, your loss tends to linearly or near linear, right? Like as a decay, right? Or at least like tries to go down. So in the one that you showed for the text image models, right? Probably when it was 760 million, right? And then we see when you scale to 7 billion as well, right? The loss, or at least the FID score differences were pretty, like there was not very significant drop, right? So I'm just wondering if in multimodal, if there it follows like more near linear, or it is more like an exponential decay, like.
Yeah, and so this brings me back to my original point that kind of the underlying distributional properties of the data are really important. So recall how like DALL-E or Make a Scene or any of these token-based models does this. So they usually use some type of like VQGAN model to tokenize the image. And so you have an underlying lower bound of how good FID scores you can get. And this lower bound is pretty much the bound of the VQGAN model, right?
Yes.
And so because of this, your scaling laws fundamentally change, right? Like you can't have linear decrease because there's kind of a fairly high lower bound, right? So really what this is indicative of is that we're just hitting the lower bound of our tokenizer, which means that we should probably go and improve our tokenizers. And so this is kind of also why I like the chinchilla style parameterization, because it has that explicit kind of no minimum entropy of the data set. So if you plot the scaling laws for like text to image, that minimal entropy is actually the kind of natural entropy that you get from the VQGAN model.
I see.
Yeah. And by the way, FID is also not that great of a metric. I think if we look at the perplexities, I think the perplexities tell a much better story than FID. So that's kind of another point as well. If there are no more questions, I'll get to kind of the more controversial parts of this presentation, I guess. Cool. Okay, so this slide usually upsets people, but kind of my claim is that traditional niche domains of AR research are mostly dead. So things like semantic parsing, dialogue, reasoning, Q&A, MRC, summarization, I think pretty much don't exist. I mean, GPT-4 does all these almost perfectly. The next frontier in machine learning is eventually to get to mixed modal. In my mixed model, I'm saying a language model that's capable of both input and on the output being able to work with different modalities. So for example, GPT-4 is input and text, or image and text on the input, but it's only text on the output. Right? Whereas you can have like, image text input, image text output, or image text speech input, same on the output. So if you're interested in like pure language modeling research, I think the single most impactful direction that we have is something that we call the science of efficient scaling. Fundamentally, how do we make the scaling law coefficients larger? How do we increase the speed of training these models? So realistically, I think there's about five subdomains that are there, right? So the very first thing is like just purely engineering better transformer implementations. This is kind of low risk, but also low impact. Like our mean flop utilization, I think is close to 60%. So even if you do, if you write the most perfect transformer implementation, you're only going to speed things up by 2x. We're kind of looking at order of magnitude improvements. Architecture improvements is very high risk, very high reward. The kind of surprising thing is that there have been like 200 papers published on transformer improvements, and we kind of still use the post-norm variant. So it's just the original 2016 one with a slight modification. We're not using any of the efficient transformers, nothing like that. Better data selection is probably one of the most interesting ways to go. It can't possibly be optimal to be training these large models on IID data. Presumably, there are some curriculums that will optimize scaling laws. I will say there is some risk. I haven't seen curriculum learning be successful in kind of a broad domain yet, but quite an interesting direction. Better objectives, high risk, high reward. Log likelihood is like token level log likelihood is very easy to model, and there's a ton of benefits to doing so. Diffusion is interesting. I have my takes that I don't think fundamentally diffusion is going to work on text. We can talk about that maybe later, or I also have a thread on Twitter if you want to read about that. And better optimization. High risk also, I will say okay reward. I do think there are fundamental limits to how much information you can squeeze out of a sample. Where we are on that curve, I have no idea. But we are still using kind of the Atom version I guess, the fixed Atom version from a couple of years ago. And it doesn't seem like the underlying optimization method has too much to do with performance if you're able to tune the optimization in the proper way. Yeah, these are kind of the core 5 directions I think are worth focusing on right now. Are there any questions here? I think I have one more slide on some work that I can share.
So like if you look at humans, like how they are thinking, they are generally not like choosing the next word, they are like choosing the next thought to think, right? Like it's like a bunch of tokens together. I don't know like if it's even possible to quantify a thought, but yeah, like is there any like attempt to find a bigger unit other than token to train these models to predict?
So I think it's worth separating out 2 things. So it's worth separating out what we are predicting versus what the model is learning. The models, I think, from token level are capable of internally reasoning kind of, I think you call it dot level. So like to give you a very simple example of what I mean here, let's say you have a very simple piece of text like 5 + 5 = 10, right? It's not like when you hit the equal sign, that's when we start thinking about what 5 + 5 is, right? Like it's not crazy to think that models are speculatively executing on input, right? So as soon as it sees 5 + 5, I'm pretty sure somewhere in the representations it starts calculating 10, even before you hit the equal sign. So the models are doing 2 things, right? So the models per token level are trying to find a representation that optimizes the current token loss, simultaneously optimizes the loss of all future tokens, right? This happens all at once, right? So because this happens all at once, I think we're not just predicting the next token. We're predicting the next token and then simultaneously learning representations that predict all possible future tokens, right? So you can think of this as kind of like speculative execution, but for language models. So I'm not sure if it's necessary to predict something at a higher degree of abstraction. I think the models kind of do this by themselves. Does
In
that
the like this, yeah, that makes sense. In the sparks of AGI paper, they like consider that the models are like specifically incapable of planning ahead. Like if you tell them like what the last token is and like the first, like, they can't make up, right? So I thought like one of the reason was that because since they are predicting the next token, they are incapable of like thinking again the 4 or 5 tokens ahead. So like that's what I understood from the paper. I'm probably wrong, but yeah.
Yeah, I mean, I don't think that's necessarily true. I mean, I think I mean a very easy experiment here is to just to do linear probing, right? You can do linear probing throughout the whole sequence for whatever target you have, right? Not being able to reason, whether that's an issue of we're not at the right scale or we're not at the right size of model, I think is kind of a more important question for me. Let me put it another way. So if you think about reasoning as some sequential steps in some arbitrary latent space, right? So for any transformer, there is an upper bound on how many kind of sequential decisions you can make, right? So that upper bound is just context length multiplied by depth of the network, right? So for any transformer, I can arbitrarily find a task that the transformer will not be able to solve because it requires n+1 reasoning steps, right? Now the question, of course, is that humans are also bounded by kind of physical constraints, right? So what is that sequential reasoning limit that humans have, and are language models at that upper bound, right? So, for example, for code, I think we can probably do with slightly better architecture. Something like universal transformers would probably work a lot better on specific code tasks that, for example, require like loop unrolling in order to predict the next token, right? For text, I don't know. And the other question is, the easiest thing to do here is just to increase context length, right? And not increase depth of the network. So if you have like a 32K context length, like some of the GPT models have now, are we really upper bounded by this number of sequential decisions that we can make? My guess is probably not, and that this is just an issue with training these models properly. We do have also experiments internally, and the reason I say that models kind of do this optimal allocation of compute within its latent space, this speculative execution, is because whenever we try to remove any type of compute in these type of adaptive compute settings, we always do things worse. And of course, like it might be possible we just don't have the right adaptive compute angles, but it seems like these models are optimally allocating compute between predicting the current token as best as it can versus predicting all future tokens. Again, this is all gut feeling. I mean, these are, I think, awesome directions for analysis papers. But this is my own personal view here.
One more question. Like, what do you think, like, going forward, like, are we already at the like optimum of scaling, like, or like, is it just like the start of scaling?
I don't think we're done scaling. Like, there are ways to fundamentally improve scaling laws, and that means that you can scale at your current compute budget to get better models. I also don't think we're out of I don't think we're out of tokens yet. So if you're modeling in a mixed model setting, you can get like hundreds of trillions of tokens. In current models, I think the largest open source one, Llama, was trained on 1.4 trillion tokens. So there's still kind of a couple orders of magnitude to go before we run out of tokens. So I don't think we're there yet, especially not in the mixed model space. I saw a question. Sorry, go ahead.
Yeah. So yeah, I think just to add one more point on that, probably whether it's like next word prediction and current prediction, right? Like the language modeling does both, right? So I think one of the points are the authors of Spark, like the Sparks of AGI paper mentioned that currently the language modeling objective that we have, right, that doesn't have ability to look back, like basically doing some sort of backward like editing or some way, right, in time. And that's one of the reasons maybe why it's limited with some specific tasks where it might require some, like, let's say, beliefs and things to change, right, with time as it keeps seeing information, or like, yeah. But wanted to maybe like know your thoughts on, like, do you think that's kind of like, or it's, yeah, it's something differently maybe that we are still not yet able to figure out.
Well, you're able to look back with attention, right?
Yes, but the point was that probably you cannot. So I think what they mentioned was that you cannot do a backward editing, right? So whatever the computer like representations that you have built, right, you cannot change that like with looking at the new observation right now, right, in time, like we see the ones that are already done, right? So you at least have some sort of knowledge or belief that you are basically carrying forward, right, in a way. And maybe that sort of might be possible that the belief is overpowering the current information, and like that just, yeah, changes obviously the language, makes a language model like probably not uh, optimized obviously to reason. Yeah, that was one, I think, point that they try to mention and probably raise.
Yeah, that makes sense, right? And so I think it's also important here to separate out the training procedure versus the inference procedure, right? So in the training procedure, you always utilize the ground truth labels, right?
Yep. Yes.
So in some sense, those are correct, right? The problem, I think, comes when you have inference, right? And so during inference, you're sampling tokens, and what might happen is if you accidentally sample the wrong token, there's a cascading effect right downstream. There's a couple of ways to deal with this. One is like improving decoding methods. That's one, but I think methods like RLHF significantly help alleviate this problem. And that the model understands that it can sometimes be wrong and that you can still generate out the right output. I also mentioned this, it's funny enough, I think we were having this discussion on Twitter yesterday and today. the log likelihood objective is mode covering, right? So it attempts to cover all the modes of the distribution. And then you can imagine when you come during inference time, you have to pick one specific mode. You don't want to be mode covering. And so that's where the complexity of decoding algorithms lie, right? And that's why you get this issue like, oh, you picked the wrong token. Like you can pick the wrong token multiple times and you can't really go back and change the tokens, right? Unless you're doing something like beam search. But you can get like mode selecting behavior. And I think that's what RLHF does. RLHF, at the cost of sample diversity, selects individual modes in the data. And so I think RLHF solves a lot of these decoding issues. And I think that's probably the main benefit of RLHF, is that it's able to find modes that are aligned with human preference, pretty much.
I see. I think that makes sense. And probably this is a bit maybe. So what do you think? Like, most of the communities so far going in scaling up, right? But what do you think of scaling down, or like, do you see any probably merit or any maybe like basically potential where it might be possible to scale down and still get good performance? So maybe like, because it then, like, this is my opinion maybe, but even if you train like, let's say, a trillion parameter model, right, you cannot, like, everyone won't have like compute or basic infrastructure to serve that model, right? And like running an inference cost itself is very expensive on that model. So how do you then overcome, or like, is there a way where you can go more scaling down trajectory, or like what are your thoughts on the same?
Yeah, I mean, this is a great question. So one thing that you can have is kind of going back to scaling laws, is you can have scaling laws that also take into account the lifetime of the model, right? So you can have scaling laws that say, you know what, I think this model will be used, you know, there will be 100 million inference calls to it, right? And you can take that into the total cost of compute. And so that's kind of where we start deviating away from compute optimal models, right? So sometimes it's worth not being compute optimal to be optimized for inference, right? I think the Llama 7 billion model is a perfect example of that.
Yes, I think, yeah.
Scaling down is also interesting. To me, there's a question of, is the right thing to scale down, or is it to scale up and then distill down? I don't think that's a question that's been answered yet. There's also kind of this implicit assumption that kind of the community has been working with, which is that training and inference are kind of symmetric procedures, right? The idea being is that you have a large model during training, and that means you have a large model during inference. Like, that doesn't necessarily have to be true. It might be true that you need a large model during training just because a large model parameterizes a space that's more efficiently learned, right? And then once you learn it, it's in a good enough space that you can do kind of much lower dimensional inference on. That I think is possible. I think like quantization is an easy example of that, right? But I think there's a lot more work to be done. Like I'm sure you could distill down, like if you have enough compute, my guess is you can distill like this, like the 70 billion or 65 billion llama into 7 billion with better performance than the current 7 billion is. Like I'm sure that's possible.
I see.
Yeah.
Yeah, because I think yeah, I have experience with like NLLB, the one that was released by Meta, and yeah, their distill model is really good. So they distill from I think 54 billion to 1 billion, and yeah, the model performance is like I think under 1 blue point, like we see from the best models. So yeah, it is definitely very well.
Yeah. And like another thing that I've seen happen quite a bit is you can remove attention hens after you train a model. So like some folks here have been playing around with taking a model that just a standard transformer and then fine-tuning it to be the multi-query version of the of a transformer, which pretty much is like significantly more efficient during inference, and just has like less heads. And so that works, right? It actually works quite well. So I think there's a ton of work to be done there. I think we need to break this symmetry between training and inference. I think they're two fundamentally different things.
Like, do you think like in the future, like the models will be fine-tuned for a specific task. Like for example, if a bigger model, and like we only like extract the model's capability to summarize text and discard everything else, and like then that would be one way to distill model and achieve only the capability we want to use.
Yeah, yeah, for sure, right? Like if you want summarization, right? You know, like GPT-4 does great summarization. I mean, you can't do this. I don't think it's allowed, like, in their contract, but you can generate a ton of summarizations and then feed it to a smaller model, right, to get very close performance. Like you can definitely distill out specific tasks, for sure.
Yeah, I think one good example of this is I think self-instruct paper, right, which kind of does
Yeah.
a distillation over GPT-3 and like shows that it can like perform good.
Yeah, and I think there's another one from Omar Levy, like unnatural instructions is another one.
Yeah, I think true. Yeah, there's been I think 2 or 3 works around us where they use model to generate instruction tuning data sets and get really good performance. So I think there was one question. So do you think like scaling, maybe better data selection is one thing that might provide a shortcut for scaling down in one way, or like, yeah, like
Yeah,
what?
absolutely. And so this is kind of our current research that will be coming out very soon on data printing. So this is pretty much showing that these graphs kind of don't make sense yet. They'll make sense when the paper comes out. But the core thing that we're seeing here is that we can significantly reduce the amount of data needed. And this is the validation set on MMLU. So it's a pretty good measure of how good the model is doing on downstream tests. So we have some new methods that will be coming out that are pretty much as competitive. They're as competitive as cutting out a lot of data. So pretty much we can, as you can see, we can cut out maybe like 10% of the data with very, very minor changes. And we can even cut out 80% of the data and still have like I don't know, something like a 30-point perplexity improvement over just randomly cutting out data. So this is some work that will come out quite soon, kind of in the next couple of weeks. So definitely data is, I think I put kind of, I think the best choice here, kind of standard risk, high reward. So definitely agree. Data is a very good research direction here.
So I was just wondering, so did you also try any like different objectives and see any different behaviors, or like maybe in one, maybe your preliminary experiments, or yeah?
Objectives like language modeling objectives, or
Yeah, language modeling.
yeah. So actually, I've completely moved over to using the CM3 objective,
Okay.
the causal mass objective. We didn't really highlight this in the paper, but if you go into the appendix, there's a whole section about how like the CM3 scaling laws and the standard left to right scaling laws are exactly the same. So you can kind of for free get infilling. So we've been using that in kind of all the areas of research that I have influenced within our team. And it works quite well. You get infilling for free, which is very useful. It allows you to do kind of these like noisy channel re-rankings. If you go look at the encoder paper, right, there's a couple of tricks there. So that's pretty much the only objective that we've tried. We've done some research to try to get diffusion models to work for text. It was a big pain. We couldn't get much work in there, and I think there's good reasons why diffusion is not super aligned with reasoning.
So due to the like latent space constraints, or maybe there are some fundamental different reasons, like for diffusion models to not adapt well to text problems.
Yeah, so I mean, so in order for you to do reasoning, you need to be able to ground on the problem, right? And the issue is because diffusion models diffuse kind of equally over all tokens, you don't actually ground on the problem, right? So the example I had on the Twitter thread was, again, let's take the 5 + 5 = 10, right? You can only start learning to do kind of the arithmetic for 10 when the support for all the tokens 5 plus 5 equals in the diffusion process doesn't overlap with any other tokens, which can be quite late in the diffusion process, right? So because of this lack of grounding, I don't think diffusion models can reason. Also, you could say, like, I think Lucas Bayer was saying that, you can do diffusion models on like the last token, like 10, right? And yeah, you can absolutely do that, but that starts kind of looking like universal transformers more than diffusion models. And you kind of lose the nice controllability angle of diffusion models. Also, I think the latent space constraints are quite strict. So think about the latent constraints for large language models, right? Like if you take every layer and you plot out kind of the path that you take in the latent space, right? You have a few kind of touch points that you have to match, and these touch points are like per token. You have to create a latent space that maps to the correct token per token, but you kind of have complete freedom in the middle to do whatever you want. For diffusion models, the latent space is explicitly constrained, right? Like every jump in the diffusion is fixed, right? And then sometimes you get even more constrained models like this. I'm forgetting the name of the paper. It was Matt Lee's paper on diffusion flows. You can get kind of the path from your noise to your sample can be completely deterministic, which means that you are forcing your model to pretty much be at the specific places within the latent space. So it's unable to do this type of speculative execution anymore. It's unable to do this type of, I'm going to dual optimize current token and all future tokens at the same time, because you have very strict latent constraints. And I think that's one of the fundamental reasons that diffusion models can't reason. I make this claim, like, would you expect the diffusion model to be able to generate an image with a coherent piece of like a paragraph of text? My answer is no. If someone does that, I will change my mind. But it is much more likely that a left to right DALL-E 1 style model can generate a coherent image of a paragraph of text rather than a diffusion model.
So interesting. Yeah, because I think the maybe constraint with flows is that you need to have inverse mapping of the functions, right? So whatever you path choose, right? Like the forward path, like you need to have a fixed deterministic backward path as well, right? Like this has an inverse function map, right? So which might be like a bit more constrained on when you integrate with diffusion and not just kind of But yeah, that's an interesting thought, I guess. Yeah, never thought from that perspective.
Yeah, we'll see. I might be completely wrong, right? This is just a gut feeling. Like I look at how crazy good like Midjourney V5 is, right? And yet it still can't generate like 5 characters coherently.
Yeah,
right.
That's true. I agree. I guess major probably like big problem with right now language models is to have a constrained decoding. Maybe like controllable text generation is a bit, as your model grows bigger, hallucination increases. So that's also another one more problem, which is an interesting one probably to solve, I guess. Yeah, like one interesting maybe like what are your thoughts on like hallucination? Do you think like is there a way to avoid it or like no? Right?
Yeah, so that goes back to my original point that I think hallucination is a symptom of this mode covering behavior, right? So the fix I think is within the pipeline that already exists now, right? So you have pre-training, which is learning how to reason. It learns all the knowledge, right? Then you have instruction tuning, which creates an interface with the model that humans have, right? And then you have RLHF, which is pretty much like a learned decoding procedure that minimizes things like hallucination. So I think the pipeline is there. I think you can have like you can have RLHF, I think, that will completely reduce hallucination within the model. I think it just requires a certain way to think about what hallucination actually is. I think it's definitely possible.
Let's see.
Like think of hallucination, right? can't you just simply like some sort of data retrieval mechanism like completely like negates all the problems of relation?
Yeah.
Like,
Yeah.
is there?
Sorry, go ahead.
Yeah, like, is there like any problem with data retrieval that it can't do?
Retrieval will fix most issues. Actually, you don't even need to train a language model with retrieval. You just train a language model and then you use retrieval to prepend things into the context, and that usually fixes most hallucination issues as well.
I think, but I think major issue with retrieval is like indexing and searching, right? So probably as your internet grows, like you need better methods to just like fetch the content, right? Like because there are like if you consider like the documents, right, there would be thousands of documents to compare against and then retrieve, right? So
yeah, it becomes like a fairly complex search question, and that's why I think like Bing with ChatGPT was very well positioned. I mean, search is quite hard. Doing this type of search is quite hard. But if you do have a good search engine, you can reduce these problems significantly, these hallucination problems significantly. I think that's one of the reasons it hasn't caught on in the open source community. Like, no one wants to host their own data store, right? It's quite expensive to host. Retrieval is non-trivial. Like, the amount of effort put into Bing search versus open source search is quite different, right?
Yeah, but like in the open source, like even attempt to like a plugin can't be found, right? Like there's not even an attempt to like link it to Google or something.
I don't know. I mean, like Bing plus ChatGPT is a good example of like a production level research with large language models. Production level search with large language models.
Yeah, I'm talking about open source. Like,
Yeah, you can connect with Google too, yeah. But I'm guessing that, yeah, I don't know the legality of like starting a company or something where you just use Google as a like a backbone search. I'm not sure.
this one maybe so. I think there was this one architecture probably proposed by Jeff Hinton, right? Capsule networks. Do you think like maybe do you have any intuition or ideas like maybe or at least thoughts on if that would be something like work that would work very well in scaling or like yeah or in general like if you think of like moving when we move it from transformer at least probably because I feel that right now in terms of architectural innovation we have kind of saturated or at least it's very incremental work on top of transformer, right? Where we don't have a like as big breakthrough as like what transformer created, right? So where do you see maybe like further down the research going or at least like maybe let's say potential uh, ways where maybe we could get most benefit out?
Okay, this is another one of my hot takes. So I think architecture. How do I say this? Every architecture before transformers had something wrong with it, right? And everyone knew what was wrong with it, right? Like CNNs have the receptive field issue, right? RNNs have an issue of kind of ON sequential steps during training, right? So you end up wasting a lot of compute. Transformers, I think, are one of those architectures where there's nothing that comes out as being really wrong with them, right? And kind of even better, as you scale up transformers, the cost of the transformer becomes dominated in matrix multiplications, which is what we have hardware for. So in that sense, they're kind of perfect for scaling up because they optimize directly for the underlying hardware, right? And there's nothing wrong with them. Like attention is all to all. Presumably, you should be able to learn any function. There's set level transformations. So like there's nothing that's obviously wrong with them. I hear people call out the long context length and attention. Like realistically, how problematic is that? Like if you have a GPT-3 sized model, attention is like less than 10%, less than 5% of the compute. Like it's not that expensive, right? By the way, we also have kind of a paper coming out soon showing that you can do like million token length modeling with a very simple modification to transformers. So that will come out soon. There's just nothing fundamentally wrong, which for me makes it hard to think about what will the next architecture be. And furthermore, we're getting like highly optimized implementations, right? Like the H100s are almost implemented transformers at the tensor core level. So the next architecture that comes is going to have a ton of competition.
Yeah, I guess true indeed. So one other question. So there are also, I think, some architectures proposed, right, which kind of just goes away completely from transformer attention mechanism, right? Just through mixing tokens, right? So probably they should have like the interplay of tokens, right, that you do across spatial dimension and the temporal dimension, right? Like so maybe channel dimension as well as like as the spatial, right? That matters more and that's something like that contributes to the actual added performance, right, or benefit. So you are able to nearly do as good as the transformer model. So probably one example is MLP mixers, right, which shows that with just this way you can do well. So I'm just wondering, like, if you think that is something like if we scale up, will work, or like probably the attention mechanism is something that is distinctively helping when we try to scale up. Like it's seeing some at least emerging properties in this models. Like is it attention or is it just a mixing of tokens that have a more prominent?
Yeah, that's a good question. I don't know for sure. I mean, I have seen some work that argues that you know, like attention has some sparsification effect, right? Some quite interesting sparsification effect. So you can actually pull out kind of individual tokens that you can focus on. This MLP mixer, I don't think is capable of doing that. So maybe that's something that's fundamentally wrong with MLP mixer. There's also, I think, some recent work being done that showed that for in-context learning, attention helps in-context learning look like gradient updates. I'm forgetting what the name of this paper was.
I think in context learning, I think there was some gradient descent steps.
Something like that, yeah, exactly. So there might be something a little fundamental about attention specifically here. And if it is the case, like I'm saying, the majority of compute is not in attention, right? The majority of compute is just straightforward batch matrix multiplications, right? So in that case, it becomes really hard to optimize. Like worst case, MLP mixer will be what, 5% faster at the same scale, 6% faster if you remove because there's no attention. Seems kind of minor, right?
Yeah, that's true. Yeah, I think so. Yeah, because I think probably this one paper which came out pay attention to MLPs, I think, by Google. What they used to show that like when you just like let's say so point was that by eliminating this attention, right, and having this more this spatial or channel wise probably interplay between tokens, right? And this you can maybe also reduce the parameters, right? So you can go more deeper. So maybe like let's say for example the 24 layer model, like the actual board, and they went to 32 layer model, and they were able to get good performance. So I'm just wondering if there's some like effect of depth or like in that case. And maybe after a certain point, depth is only that matters, and maybe it does not probably very has to do much with the attention block or it is.
Yeah. Okay. So actually, that's a good point. I think like the proper parameterization of transformer has been a little underexplored. So like tall and thin versus kind of like short and wide. I don't know. I haven't seen any good papers. Actually, internally, we've done some kind of ablations here, and it turns out that something in the middle, we were calling them like chubby models, actually are better. So having smaller depth but larger embedding size is better at certain scales, right? So in the dream world, you would have kind of one equation where you can plug in all your hyperparameters. Like this is like if you have infinite compute, you can create this equation, right? That you plug in all the hyperparameters and it tells you what your predicted loss should be.
Yeah.
So that's kind of I think would be like the most optimal scaling law paper, right? and from there you would be able to make architectural decisions.
Yeah. But that's kind of, I think, a bit more probably like very hard problem so far.
Yeah, I mean, there's some hope, I think. Like, I think one of the most underrated work recently has been this. I think it's Greg Yang's what this mu parameter, mu parameterization. I think it's from the Tensor Programs 5 paper. I don't know if you've seen this, but it's really awesome work. It's pretty much saying that there is a parameterization of a model such that you can tune it in a very low cost, low dimensional setting, and then scale it up, and the hyperparameters will still stay optimal. So these types of parameterizations give me hope that we can eventually get to something like that, where we can actually find the semi-optimal transformer architecture for specific problems.
Yeah, I haven't seen this, but I think I read a bit more. But I guess I think the idea seems interesting.
Yeah, I mean, I can send it to you after if you'd like.
Yeah, yep, I would love to read it. And so one more. So did you also try like maybe doing your experiments on mixture of experts? Because at least in my experience, based on interacting with different folks, it is like that mixture of experts require really like, are more data hungry because they operate more in sparse manner, right? So they require like way more data. And yeah, so do you observe any different like cases and when you try to uh, apply the same scaling laws or yeah?
Yeah, so I've explicitly never really worked on mixture of experts models. So this is all kind of hearsay from people that have been working on mixture of experts models. One thing is they're quite complicated to run during inference. So that becomes kind of a bottleneck for productionizing or for general open sourcing. The other thing is that they lie a little bit. So mixture of experts superficially reduce perplexity. And this is kind of, I was making a point earlier on that, maybe perplexity is not fine-grained enough to get, to capture like reasoning capabilities, right? So if I give you like 4 or 5 words about what I think the document is, you can reduce the perplexity a significant amount because a lot of the perplexity is concentrated in the first, 100 tokens or something, right? And so this is kind of where like retrieval models shine, because retrieval models, like, you prepend the document or something, it's quite easy to get those first 100 tokens right. So all of a sudden it looks like, retrieval models are fundamentally better because they lower perplexity during training significantly quicker. But the thing is they don't really change how well you reason. And it's hard to measure that without running downstream evaluations. And I think MOEs suffer from the kind of the same issue here. It's like the routing itself has information that allows you to reduce the perplexity quickly, but it doesn't fundamentally add anything to the reasoning capabilities. That's kind of my impression of MOE, of kind of MOE and retrieval models.
Yeah, because I think intuitively it seems that it's kind of a way to ensemble, right? So maybe like let's say not necessarily include as such reasoning component, but you can think of it as running like n different like answers, right? And you then do some sort of max voting or similar to that, right? Effectiveness partially. So yeah, so maybe it's not like utilizing one branch or the other branch to make decisions on the other one, right? So it's kind of still, if you think like those decisions are being made independently, right, and then you just aggregate those into maybe some voting mechanism or something, right? That lets us like maybe reasoning as this fundamental different trait, right? That as long, let's say you get something, right, you change your belief or like maybe throughout, like as you're doing the reasoning, right, which might not be necessarily in MOE, right? Because individually it's just different branches that are being propagated, right?
Yeah.
Maybe, but that's my maybe understanding, but yeah.
I would also look at branch train merge. I don't know if you've seen this paper.
No, I haven't seen.
I would check it out. It's kind of interesting, like domain level MOE And it turns out that you can just average the domain experts and you get quite good results. This is kind of the counter thesis to what I just said. That's another paper I would recommend looking at if you're interested in this direction.
I think I'll have a read as well.
Sounds good.
Probably, I think one of the paper that I've seen which seemed a bit more interesting was where they use some partial mixture of experts where what they do is they just pass the information in one, like as a single way, but also do some like selection, right? So it's like there are always like more than one expert selected, and then you do some sort of fusion across it. Whereas in traditional way, just like maybe depending on different cases, most of the ones use like just a switch gate, right, where you just select one expert and just like route the information.
Yeah.
Um,
Yeah, I mean, I don't think you can fundamentally beat out compute. I think that's been my take. Like, I think all optimization methods roughly are able to kind of extract out the same level of information. I think all transformer parameterizations, the classical transformer parameterization, have the same functional approximation power. So in that sense, the only thing that matters at the end of the day is kind of how much compute, how many tokens you push through it, right? And I think this also applies to MOEs as well.
I see.
Yeah, this is kind of my negative take that compute is the only thing that matters at the end of the day.
I see. So is this due to like maybe probably putting it more in Monte Carlo perspective, so where you do simulation, right? So if you do it for longer, you will eventually converge with the same results, right? So more like similar idea in this case that once you throw like compute and data, maybe probably after training for longer, it will still converge more or less nearly the same point.
That's been my gut feeling. I have yet to see anything that's like super convincing otherwise. I think the retrieval works try to get there, but my issue with retrieval works is that they don't distinguish between like surface level perplexity improvements and reasoning improvements. Like knowledge intensive stuff, sure, but that's also just cheating because you're able to pull up a document that has that knowledge intensive conditioning, right? So yeah.
I see. So one question. So probably that's like scaling analysis is like at least more physical for big text, right? But how do you see this to be like maybe at least like how academicians can pursue like more similar studies and analysis? Like in your experience, what would be a good trajectory for them? Because there's computational limits and bounds, right, that they can go for.
Yeah, scaling laws are definitely kind of, you have a lot of compute type of project. So if you're kind of like in an academic setting where you don't have a lot of compute, I probably wouldn't do scaling laws. I think there are a lot of cool. Sorry, go ahead.
No, I think there was a Cohere, I guess. So maybe you can continue.
Got it. I do think there are places where you don't need that much compute to try things out. Like I think instruction tuning is an interesting place to start thinking about how we do things. My pessimistic take here for instruction tuning is that the delta that I've seen with instruction tuning is always somewhat fixed. And so really what matters is how good of a base model you have. You will always get some fixed improvement if you instruction tune. That's kind of what I've seen, but I feel like there are much more like better ways of doing instruction tuning, honestly. Like I don't know, like the current way that we do things is just you mix instruction tuning data with some of your classical pre-training data, and then you either do supervised fine tuning or the instruction tuning way. But like there's more, for example, like there's more robust ways to do fine tuning, right? Like there's adversarial fine tuning strategies, right? Like I haven't seen those apply to instruction tuning, right? So methods like this that don't require a lot of compute but are still able to fine tune language models, I think are quite good for academics to look at. Even things like better data selection still require you to train language models. so it's still quite expensive. I think prompting work in general is quite interesting. I do question the longevity of prompting work. It seems like as you improve instruction tuning, as you improve RLHF, the kind of prompting tricks that we have will go away. But taking a fundamental look at what prompting means is quite interesting to me. Like one argument that I really like is that chain of thought prompting is really a method of adaptive compute. I think the original paper looked at this a little bit, but that's quite an interesting research direction. Some of the scratch pad work is quite interesting as well. Yeah, I mean, there's a ton of stuff I think for academics to do. Like, not every project has to be a high compute project, right?
I think that's true. Um, so one more, just like one last point. So probably I just wanted to like see, like did you do any other analysis probably where let's say you can probably connect scaling loss to OD performance or some way? So is there any like good neat way to maybe let's say whatever your scaling loss might be, right? To also connect or distribute with maybe like OD performance on certain things.
So the question is like, are there scaling laws kind of in different domains than the ones that have been explored?
No, so I think what my question was, so let's say right now you train the model, right? Like pre-training, right? So you train it on almost like general domain data set, right? And maybe let's say probably when you try to adapt the same problem with some specific data set, right? Or maybe, for example, let's say if you think of vision, right, as a problem, right? Like so in that case, you train on certain images, right? Like of certain color scales, right? And then you change color scale, right? So the problem essentially the task is still the same, but now the data is OD, right? In that case. So do you see like any connection between like scaling loss and OD like in some way or the other?
Yeah, okay, so this is a kind of another place where I think I have a hot take, right? So when we talk about out of domain, like what does out of domain mean when you're pre-training? Like if you're pre-training on Common Crawl, right? Kind of all of them, a random sample of the net, right? What domains would you expect to not be there that you would consider out of domain? Like I think it's hard to think of any domain that would not be on the internet that's interesting to humans, right?
Yes, true.
Yeah. So in that case, when realistically, what we're talking about is like, was the performance on domain is maybe not the right word, but like tasks that are in low quantities, right, on the web.
Yes.
That's quite interesting. Finding connections between kind of this quality multiplied by quantity metric in the pre-training data and downstream performance, I think is quite an interesting research direction. Yeah, I don't have much to say. I haven't seen anyone really do this. I think there's a hint here that, I mentioned that, OPT and Llama are surprisingly good at multilingual, even though they weren't explicitly trained to be multilingual.
Yes.
So that kind of shows how good these models are at extracting out data from very small quantities of information. I would also take a look at, we had this paper called Memorization Without Overfitting. I'm not sure if you guys have seen this paper, but we kind of make this argument that, as you scale up, it becomes easier and easier to memorize things, like with our definition of memorization. But kind of, I think at like the 13 billion scale, you need to see an example roughly 10 times before you can memorize it almost completely. And so what we extrapolated out is that, at 175 billion, you would have what we call this like intra-batch overfitting, in the sense that you need to see an example once in order to memorize it. You see it once and you memorize it, right? At a large enough scale. So if this is happening, I think it kind of has ramifications of what we call out of domain, even though I don't think domains really exist when you're touching like, 2 trillion tokens from the web. I think you're bound to see something that's in domain.
I think it has to more do with like maybe out of domain tasks rather than like cutting data, maybe specifically, because I think it's very high likelihood that I might have seen data, but maybe not necessarily like knows how to do the particular task with. let's say the data that has already seen, right? Like, for example, it has just right now seen like an expert prediction rate, right? I can just use the same data and pose a different task out of it, right? So that's like more in out of domain or it was zero shot kind of a way.
Yeah, and that's actually kind of like having a taxonomy for these tasks is quite complex, I think, but could be potentially very useful. It's hard to understand, like it's hard to understand interpolation of tasks versus extrapolating out a specific task, right?
Yes.
Like I don't know, GPT-4 is quite good at different chemical synthesis tests, right?
Mhm.
It probably saw this in the data. Is it extrapolating out from its data that it saw? Probably, maybe. I have no idea, right? I don't know how much of this type of synthesis data is available for free on the web, right?
I think that's true, but maybe like it's kind of like that GPT might have seen entire web data, right? So there's maybe some probability like that similar instances or at least nearly similar examples might be present, right? Or at least which kind of mimic or at least have the same
Yeah.
effect. So,
Yeah, and then that's the question of it. Is it a zero shot task at that point? Like I think zero shot has become kind of a very overused term, right?
yes.
So it's not really a zero shot task, or like like there's alpha codes was really good on some tasks, on some writing some code for problems that it hasn't seen before, right? But is that really extrapolating out learning how to code, or is that just an interpolation between all the code problems that I had seen before?
Yeah, I think that that's true because there was this one probably study or I think like where authors probably tried like the lead code problems which were released like before GPT-4 announcement and ones which were probably proposed after GPT-4 announcement. And model was like struggling with the problems which were like probably formulated after GPT-4. So there was some like maybe like probably over a spurious correlation or memorization happening in internal within the parameter space. Probably.
Okay, yeah, that makes sense.
Yeah. Recently, I saw a paper that said like GPT-4 is apparently better at annotation than human themselves, and I was like, how do you even know? Like after like so much, like because the training data was not cut, like the data on which they were testing the GPT-4 on was not was before 2020. So I was like, how do they even know that the GPT hasn't memorized all of this already? And this is like a fresh sample.
Also, one thing to keep in mind is like GPT-4 is a product, right? Like we don't know what data to train on and what data it didn't train on, right? So it's kind of hard with these studies. The only thing you can do is pick some data that appeared after a cutoff date, and then you have to dedupe that with the rest of the internet, which is kind of also a non-trivial task.
Yeah. So one thing maybe like just a curious question. So how do you differentiate memorization versus overfitting, right? Because I think like that's very like gray area, right? Or at least like line which is not kind of proper, or at least depending on like let's say your interpretation, the line might change, right? But in what is memorization and what is overfitting, right? You would consider some things which are memorized as like to be good as well, right? And some things which are memorized like to be actually hurting the model, right? So how do you define like basically like a difference between both?
Yeah, it's very hard, right? Like in our paper, we define memorization as like being able to recall certain percentage of tokens given a certain prefix, right? It's a very classical definition of memorization. Overfitting we define as perplexity on a dedupe not seen validation set. And so kind of what we saw was that larger models are capable of memorizing more of their training data before they start overfitting, which makes sense. So it seems like they're able to extract out much more high level and abstract patterns than smaller models. That was from our previous paper. But yeah, memorization I think is actually quite hard of a thing to
Because
quantify.
yeah, maybe like at least my intuition is that let's say some things might be very easy, right, for particular language model, right? And if like language model does better or at least like intuitively learns that, right? That might not be termed as memorization deficiency, right? Like specifically. Like the problem is it's very simple so that the model is able to pick it out automatically, right? And not that has to do with like the like this training, maybe over parameterization, which kind of just like learns and fits to the space, right? So maybe it's very probably hard like area, or at least like if we look at just the standard definitions that are out there, right? If you recall, K% of tokens, and yeah, maybe the point is that let's say certain examples might be harder as well, right? And certain examples might be random as well. In both cases, if we see the perplexities would be higher, right? But it's still there is a distinction, right? Like certain examples are hard, like which have higher perplexity, and certain are just randomly composed tokens, right? Like where nothing learning or nothing contributes, right? So it's very hard, right?
Yeah, I mean, there are some approaches to try to like unravel the difference for high perplexity samples, right? Like one thing that was proposed, like we call it delta perplexity. I think contrastive decoding methods use this all the time. But like if you subtract the perplexities from a large language model and a smaller language model, that is usually an indication of whether or not a data point is good. So for example, if you're modeling like, hashes, right? It doesn't matter how big a language model is, it's not gonna learn the hashes, right? It's random, right? Unless it learns the hashing algorithm, but presumably that can't happen, right? So because the hashes are random, the perplexity differences between two differently sized models is going to be 0, right? It's going to be the same maximum entropy. If you have a sample that's hard for the smaller model but easy for the larger model, then that means it's a good sample, right? It means it's a hard sample, hard but learnable sample. So there are ways for quantifying what is like a hard but good sample, and then there's the question of like if a sample is only learnable at a certain scale, like do you include that when training a smaller model, right? Right, like you wouldn't be giving calculus problem to like a third grader, right?
Yeah.
So yeah, the data direction is super interesting.
Yeah, I think that can be hit a lot with data related things. So far, it's more, I'd say, like at least a standard like approach has been that you just like collect all the data and like throw enough compute so that the model can generalize. But I think maybe that there's something interesting in data that, let's say, you can get away with pruning data and still like get similar performance. So by eliminating all these chunks, right? And that's where maybe we might be able to have some sort of like carbon efficiency considerations in mind, right? Like by just eliminating all this unnecessary tokens or like things that hurt the performance.
Yeah, for sure. Yeah, I think data is the most likely direction to get an order of magnitude improvement scale, I think. But that's the only one that I'm confident is possible.
Yes, I think, yeah. Like the others are a bit more hard, right? Like we don't like know a good way to model few things, right? So at least maybe some better objectives or things. Right? So at least those are currently stagnated or at least have reached some bound, right? Like maybe unless we come up with something really different. But data is still like there's still like effort scope for like let's say doing this thing more in data filtering and selective like training, right? Because that's still like very unexplored, I would say, area comparatively.
Yeah, absolutely. There's a ton of good work to be done in data.
Yes.
Yeah. And by the way, we're now running out of tokens, right? Like if you have a mixed model setting, we have more tokens than we can train on. 100%. We're now running out of tokens. So
I think true. Ideally, I think if you even have like a unimodal model, right? Like essentially, if you look at, you will still be like good with tokens, right? Like because we won't like reach even the optimal data usage at a point, right? Right now with the current hardware that we have, so, or at least like the trade-off would be very like the amount of time it would take for training, like with showing the entire data, right, would be very high, right? Like for example, if we consider GPT-4, right, I suspect that they might have probably used the entire internet, right? Like at least one way to think of. But probably the training related, if you look at, right, it might have taken like way longer, right? So probably it is still like bounded by certain computer limitations, right? The data that you can still process, right? So think maybe we might never like completely exhaust the data. Data will keep generating, right? Like so, there's a like it's a never-ending process, right? So yeah, I don't think maybe that's my pessimistic view I think right now, but yeah, maybe we might not be able to cover the entire internet. Like, but yeah, what would be your take on that?
Um, yeah, and the question is, do we even want to? Um, like you said, there are compute constraints, right?
Yeah,
And all of the data is not good data either, right?
yeah.
So I think data printing is going to become a lot more of a mainstream thing, like very soon.
Yeah, I think so.
Um, like I expect to see like analog neural networks like by IBM, like to like change the computation field at least somewhat. Because right now, like there's like very roundabout way of simulating networks. Like why not just simulate them directly?
I mean, like the H100s are pretty direct, right? For transformers.
Yeah, yeah, but like the IBM's, I read the IBM's new paper on making analog chips where they are storing weights by the resistance of the element, and that like the resistance is like changed by the number of electrons they are pushing in, and so that way the entire thing is analog. So like there's like literally almost zero roundabout way of simulating things. Like even now, like the gates are like completely unnecessary um, to do what like the networks are doing at the moment. So like once those thing comes out, I expect to see competition, neural network competition, to get much cheaper.
Yeah, I'm sure hardware will keep getting better and better for sure. So it's a
Yeah,
race between data generated versus hardware, right? At this point,
like
um,
what will be the bottleneck first?
I have no idea.
Yeah, on another thing, like I also read a paper about like how to test models that have stepped the entire internet. So they created a fictional data set. Although those they said it like fictional, but it was more like future, like in 2030, the president is this, and then they are testing it. Those kind of ways to test a model that has like seen everything. I think another better way to like create a fiction instead of projecting future, because you can expect other people to have like made prediction about 2023, 2030, and the models might have taken that. Like creating an entire fictional world to test a model would be better idea. And also I expect like in the future they are not even going to release the data set. There are like API, and you just send the model, they test it, and they just give you the score. They don't even release the data set.
Yeah, yeah. I mean, yeah. Testing these evaluation of these models is really hard. Like realistically, when you're training a large language model, it's something like you spend 60-70% on data, right? You spend like 30-20% on evaluations and maybe 10-20% on actually training the model. Evaluations are really, really hard to do. That being said, like I think reasoning is a fairly abstract and learnable thing. Um, like I'm quite surprised how well GPT-4 reasons, and I think it'd be hard to come up with a realistic task that GPT-4 would consistently be failing on that also was a useful text task. Um, so I think from that sense, that type of evaluation is done, um, unless we can discover something that we think GPT-4 right now can't do. Mixed modal evaluation is kind of behind. Like getting like really good grounded and like general VQA is quite tough to do actually. So I think the mixed modal evaluations are personally my interest now. I think there's still a good amount of headway to be made.
So I think one of the main problem with like at least mixed model models is like it's also more compute hungry, right, in certain aspects, or at least one. Also, probably if we look at, let's say, even if we want to have a good benchmark, right, or at least ways to evaluate the model, right? So at least there's more effort in terms of like you generating and building data sets as well, right? That qualitatively measured with different aspects, right? Right now, if we look at it's just one accuracy or like just one end product that we care, right? But we don't like actually evaluate, let's say, how the entire prediction or at least is done in like steps, right? When we think of reasoning, or at least what sort of small components are being involved, right? So I think that's something that would be interesting to see. Like I think I don't know if you have heard one paper known as Viper GPT. So probably that was I think one paper which was like at least bit caught my eye because like it kind of breaks down the actual task in terms of reasoning steps, and I see that to be really good way of evaluating maybe models like how good they behave like or like are because you can then like split all this like let's say the entire prediction into small steps, right, and see where the model actually is making mistake and like go back and maybe fix or like at least come up with some better ways, right? I think I dropped the link for the paper, but yeah, that was one like really interesting one. So the point was that if we can use such ways like to maybe like let's say as a reward function, right, in the model, like when using RLHF, right, then that might itself like
Yeah, evaluation is hard. I mean, so for example, at the beginning you said like mixed modal evaluation is usually more expensive, right? I mean, it doesn't have to be, right? Like MMLU is mostly like perplexity based re-ranking of question answer pairs, right? Like you can do the same with VQA, right? Like it doesn't need to be open-ended VQA. You can have multiple choice, right? There's also work on like adversarial data sets that are quite easy for humans, but are quite hard for machines. I think that's also quite a good direction for these types of evaluations. Like I think there's like this adversarial NLA. I think it also came from Meta.
yes.
Yeah.
Also, I think Winogrand challenge is also like really good.
Oh, no, Brown, yep. Yeah. Evaluation is really hard. Also kind of underappreciated how hard it is to do proper evaluation.
I think yes. Nowadays I think with like it's more evaluations that are like I would say it's kind of sometimes a bit vague or at least very cherry picked. Where you see like this model is like really good and good, right? There are still potential gaps and like yeah, or maybe evaluations are inconsistent. So maybe head-to-head comparison across different systems might not be correct, right? So that's also one thing I think. Yeah, like it's just every time everyone is in the race of getting SOTA. So yeah, but I think yeah, there are definitely I would say certain benchmarks are definitely interesting, but like with this bigger models and like GPT-4 similar like models, right? Like those benchmarks will also become maybe let's say obsolete or at least near solvable, right? Given performances, maybe a year or so.
Yeah, I mean, also another thing to kind of keep in mind is that like zero-shot evaluations are very, very hacky. Like very, very hacky. Like the difference of whether or not you put parentheses around the question or around the answer, like a parentheses or no parentheses. For certain models, there's like a 8-point difference on MMLU, right? So what ends up happening is that if you want really, really good numbers, you end up having to hack, you know, you have to move around the prompts a little bit, right? So it ends up being hacky. It's not really a I mean, like instruction tuning fixes this, but the evaluations that I've seen for LLMs are pretty bad usually. They're not consistent. So yeah, I think there's definitely going to have to be more work done on how we evaluate. Like MMLU and Big Bench are good starting points, but we're not there yet.
I think yeah. True. Any other questions from anyone else? I think we over like the time by an hour. But I think yeah, it was really good discussion and more I would say like interactive session where like yeah we kind of discussed some problems and like yeah like was interesting to hear your feedback. And at least I've heard like really different perspective from what other people have like for some of the problems. So it was really good. Like never talk from that perspective. I would say like
Um, yeah. So last question. I don't know if it's like a fair to ask you, but there was a survey like a couple of decades back, in which they were asking people when will certain AI milestone will be covered. For example, Turing test, when will Turing test be covered, and when will the research level AI will be covered, and like when will the superhuman AI will be covered. So the most chosen response for all those things was like they will never happen. And the second most chosen open was that will happen. They will happen in the 2020s to between 2030s. And like just the start of 2020, and we are already past the Turing test. Like a lot of time, people in comments and Twitter, they write GPT test and like very organic text, and the line at the end they say, okay, this was written by GPT, and I'm like completely perplexed. Like what the hell? So like Turing test is already covered. Do you? I don't know if it's like fair to ask you, but considering you are much more closer to that area, do you think like when will the other milestones will be covered? And do you think I should even like go into research, or will it be redundant in future?
I will say, if you're passionate about doing research, you should go into it. Um, there are still a lot of kind of questions to be answered. The kind of sad thing, even for me, from a research perspective, is that a lot of the problems, even kind of in a mixed model space, don't require much creativity anymore. Like the recipes that we have with large language models seem to be general enough to apply anywhere. So I think everything that we've seen happen for text will happen for image, speech. I mean, we see with code, but for molecules, I think most modalities will have kind of GPT-4 like moments soon, very, very soon. The one place that I would say is kind of the final frontier of there's uncertainty about what will happen is domains that don't have a lot of data readily available. The first one that kind of comes to mind is robotics. So the kind of, I think, next big splashy, really, really big and splashy moment will be when we have something the equivalent of large language models for robotics. I think that's kind of the final frontier for us. I don't think the big milestones for the other modalities are that far away.
What do you about RL? Like RL has always been lagging behind other fields, even
Yeah,
though the deep, yeah.
I mean, RL for like games specifically, you mean?
Yeah, like on general, RL is like lagging behind. Like there are no foundation models in RL. Like the latest one, which was released by DeepMind, which they like advertised as foundation model, like was essentially useless for anyone doing anything like useful. So like RL is something which is yet to be, come even close to that kind of thing.
Yeah, I mean, RL kind of had some big moments, right? With like AlphaGo and those others. I will say the impact of these fields is proportional to the amount of data that it's had, right? Like, I think unsupervised learning has been big for so long just because there's so much readily available data, right? Supervised learning is kind of also making a comeback thanks to like SFT or instruction tuning. RLHF, right, for language models. And even if you look at things like AlphaCode, like the large scale self play is very reminiscent of pre-training, right? Yeah, in that sense, I would say like if you have a general purpose like mixed modal agent, presumably it should be very easy to get them to play a game, if that makes sense, right? Like
Yeah.
for me, RL is like starting from scratch from every RL game seems kind of weird. And I know people have done like initializing with pre-trained pre-trained image backbones, right? And supposedly that helps, right? But having one agent that has a general and grounded understanding of both the world, I think, which will kind of bleed over into games as well, is probably the next step before there's kind of a very general purpose RL agent. I assume you're referring to like Gatto, right? Are you?
Yeah, exactly. Yeah, like there's also Deemer V3, which does not require hyper parameter tuning much. Like they did like state of the art on Minecraft.
Yeah.
Yeah.
Yeah. So general purpose like grounded agents, I think are the next step. And I don't think we're too far away there. Like there's no obvious walls there, right? It's like just collecting a large amount of data and then pre-training it, and like in the way that we're proposing to pre-train it, I think is a very likely way to work.
So I should start plumbing. Yeah, like that's like the only field left.
So there's still a ton of work I think to do with like things like how to properly chain things together, right? To get non-trivial behavior is quite interesting, right? I mentioned like fields where there's not a lot of data will require some major
Yeah.
analysis to work, right? So I mean, getting into the large language model game now, I think that's where your concern is most likely at. Like sometimes it feels like I get this from academics quite a bit. Sometimes it feels like it's hard to compete with the big companies. But that's sometimes also kind of a benefit. Like you don't want to directly compete, right? Like you take research that or that big companies wouldn't necessarily do, right? And that's where you can be quite impactful.
Yeah, this is like the most like very insightful conversation. Certainly.
Yeah,
Thanks.
Thank you.
do you think maybe there's like a likelihood of like something, let's say, as breakthrough as like transformer or some innovations like kind of let's say primarily coming from academics right now, because those are the problems that academicians can work more on, right? Like if we first try it and tried it as well, then yeah, because I think mostly the industry thing is like the scaling on the right. That's I would say at least a trajectory that every problem has been applied.
Yeah,
Or like if you
exactly. So
pursue it.
yeah, exactly. So high kind of projects that have high risk, very high risk are ones that you can take in academia. So there's kind of a chicken and egg problem. Like personally, I would never scale anything that hasn't been tested before, right? Like the last thing you want to do is waste like tens of millions of dollars of compute on something that hasn't been battle tested before. And that's maybe one of the reasons why we're still stuck with some of the older transformer implementations, right? So it's kind of up to, I think, outside of industry or outside of these big labs for people to convince that it's worth looking into, right? I think the efficient transformers kind of muddied the field a little bit because there were so many that were published, and like to be honest, none of them scale well, right? Like it's very easy to say like this low rank approximation works on small scale. Like yeah, of course it works on small scale, right? Like at the beginning of training, you learn low rank approximations, right? But all the interesting stuff happens when you have like very high rank matrices, right? So a lot of these like very efficient transformer implementations of like attention don't really scale. And so this is experiments that we did and kind of didn't necessarily waste compute, but we spent a good amount of time on it, and it turns out it doesn't work, right? So those types of like very high risk things are I guess I would say I think it'd be quite rare to see a big lab dedicate a large amount of money to try to do something like this. And hopefully I'm wrong, but that's been my pattern that I've seen.
Yep. Yeah, hopefully I think you're correct. So there are some problems that can be done by us, which in future or at least come from academic. Because yeah, right now it's like all big companies like if you see like just everyone like big companies are the one who are like hitting like big breakthroughs, right? It's just like academics have like right now very little or like no play at all. Like in if you look at like the large LLMs or things. So yeah, but let's see.
Yeah, there's definitely a ton of problems. Like, there's no reason to get super like narrow focused on large language models, right?
Yeah.
I mean, just think about like everyone ran towards GANs, right? And think about where we are now, right? So there's going to be some there's a lot of interesting research directions adjacent to large language models.
So, what comes next?
Sorry.
So yeah, are there any? No, I'm saying like yeah, that's true. I would say. And let's see maybe what comes next. Like that kind of completely shifts away the field, or at least the directions that we are going in right now. Yeah, maybe something more different and like probably more at least efficient.
Yeah. So any new approach just needs to be one that scales better. I mean that's the test, right?
Yes. I think having like more scalability factors is definitely important. It needs to be adopted widely, I would say. Otherwise, it would be just like one other paper on the internet.
Yeah.
So I think yeah, maybe we overshooted I think by an hour. So probably if there are any other questions, then I think we can continue. Otherwise, because you might also have some your other meetings or commitments as well. Right?
Yeah, I just want to say thank you.
Yeah, of course.
Yeah, like this was I think maybe the attendance was low, but I would say like one of the most insightful discussions probably I would say so far we have
I'm
had.
glad.
Like, we look forward to having you more. I would say, like looking forward to what comes next from your group.